Hi, I'm Peter Rowlett.
And I'm Katie Steckles. And Peter, what's today's mathematical object?
Well, today I have a lottery machine. Now, you might imagine this is a huge sort of room-sized device, the sort of thing that does the National Lottery. But what I have is a small metal wire turny thing that you turn by hand. And
right.
I think it's sort of lovely because it's got this very physical thing going on.
Yeah, like a little cage.
Yeah.
Yeah.
Yeah, like a cage full of balls that spins when you turn a handle and one of the balls falls out. And it's sort of, I can't remember which shop, but there was a shop having a closing down sale and this was in there. And it's a drinking game. So you see it's got these hoops on the side and they're for putting 6 shot glasses in. And
right.
Then there are 6 different coloured balls and there are 48 balls in total. And I guess because they want it to be a multiple of 6, so that it's equally likely you choose whichever of the shot glasses. So the idea is you pull a ball out and you drink that drink, and that's a game somehow. But I bought it because it was extremely cheap and in this closing down sale. And then I got it home and realised that it doesn't exactly work as a lottery because it doesn't have numbered balls. So then I wrote little numbers on all the balls.
Wow.
I first counted them, and then I wrote numbers on them. And of course, some of them are black and dark blue, and then you can't see my black pen on there. So some of them have the numbers written on in Tipp-Ex. It turned out to be this enormous faff to arrange.
Good. I mean, assuming none of this kind of affects the weighting of the objects and how likely they are or not they are to go. If they've got lots of Tipp-Ex on, they might be heavier, so they might be...
Maybe so,
I don't know.
yeah.
It's probably not that precise.
And then sort of the cage has a kind of hatch to put the balls in it, and then it has a little scoop thing that as you're turning it, one of the balls falls into the scoop, and then the weight of that means that as it comes round, it turns to be on the outside, and that one gets spat into a little channel. And it's a sort of lovely little mechanical device in that way. Anyway, I thought it would give us an opportunity to talk about lotteries and counting problems and things like this. The reason that I bought it really was I thought, oh, that's sort of a mathematical thing, and in the spur of the moment I'll buy that. But I've run it a bunch of times with like year 9s through to undergraduates, doing sort of combinatorics and probability and lotteries as a sort of workshopy thing. A normal lottery machine, a sort of standard lottery when people just come up with a hypothetical lottery, has 49 balls. And mine has 48, which is a slight niggle. Although, the UK National Lottery doesn't have 49 balls anymore, it used to. But it seems to be the standard default number of balls for a lottery is 49.
Why?
So there were lotteries in Genoa in the Middle Ages, which were analysed by Euler, which used 49 balls, and people just seem to sort of copy that system. Which is sort of interesting. What you kind of need is, you need for the number of balls to give you a good probability of somebody winning, given however many people are likely to play your lottery.
So it's a square number, so if you wanted to write the numbers down in a grid, you could do that in a square, so maybe that's why.
Maybe so.
So it's a big enough number that it's, that it results in some interesting probabilities. If it was too small, you wouldn't have that many things to choose.
Yeah.
But it's a big enough number, but it's not so big that it's unwieldy.
Fits nicely on a lottery ticket, I don't know.
Yeah.
So... the thing to think about with this is that although it's a cage with a nice mechanical operation and you turn a handle and all that, effectively it's a bag from which you're lifting a ball.
Yeah.
So if you have 3 balls in a bag labelled A, B and C, and you want to pull them out into 3 boxes, for the first box you have 3 options, because there are 3 balls in the bag. You pull one of them out and put them in the box. For the second box, you've now got 2 options remaining, because there are 2 balls left in the bag. So you pull one of those out 2 different ways and put it in the second box, and then the third box has to be the third item there. So the number of ways of drawing 3 balls from a box in order are 3 times 2 times 1, which is 3 factorial. That's where factorial comes from. Then 3 factorial is 6, of course. So the number of ways of arranging n objects is n factorial. That's fine. But we're not quite doing that here. We're not just arranging the 48 balls any old way. We're doing something a bit more complicated than that. So say we've got a bag with 10 numbered balls in, and we want to draw 3 of them. Well, there are 10 options for the first ball, and then once you've drawn the first ball, there are 9 left in the bag, so there are 9 possibilities for the second ball, and then 8 possibilities for the third ball, and 10 times 9 times 8 is 720. So there are 720 ways to choose 3 balls from the bag of 9.
Yeah, so it's part of a factorial, right? You start doing the factorial and then you stop at some point when you've got enough things.
Yeah, so in order to do that, if you wanted to express it using factorials, 10 times 9 times 8, you could say that's 10 factorial divided by 7 factorial. And the divided by 7
cancels all of the smaller ones get cancelled out by the things on the bottom, yeah.
Yeah, absolutely. So it just gets rid of all that 7 times, 6 times. And the advantage of that is that you, if you've got n balls, you don't have to do n times n minus 1 times n minus 2, which is a bit ugly. You can just do n factorial over n minus 3 factorial or whatever it is. So then, thinking about lotteries, we don't actually care what order the balls come out of the machine.
Yeah.
That's sort of not how lotteries work. So within our 720 ways of choosing 3 balls from 10, there are loads that are just going to be rearrangements of each other.
Yeah.
And depending on circumstances, you might care about those rearrangements or not. In the case of a lottery, you do. So those 3 balls that we've drawn out, we already know the number of ways of arranging 3 balls is 3 factorial.
Yeah.
So we should reduce our 720 by a factor of 3 factorial if we don't care about the order they come in. So what you've got now is you've got 10 factorial divided by 3 factorial and 7 factorial, the bottom half of that fraction.
Right.
For drawing 3 out, and 720 divided by 6 is 120. So there are 120 ways of drawing 3 balls out of a bag of 10 if you don't care about the order in which you draw them.
Yeah, and you can obviously scale that to any size of lottery by just changing the numbers.
Yeah, so if you had n balls and you wanted to draw r of them, then you've got n factorial on the top of your fraction, and on the bottom you've got r factorial, which is the number of rearranging the r's. Let me say that again, because I'm going to have to let the cat out of the room. She keeps jangling her bell and... I've done some approximation of closing my door. Oh dear. So if you've got n objects and you want to choose r of them, then you've got a fraction, the top half of which is n factorial. The bottom half is n minus r factorial, which is cancelling all the lower terms. And also on the bottom half of your fraction is r factorial, which is the number of ways of arranging the r once you've chosen them. And that object, n factorial over r factorial n minus r factorial, is the binomial coefficient, and it's often called the choose function, and it's just often written, n choose r, n over r in brackets, or nc r, or something like that.
Yeah, there's like 10 different ways to write the choose function, aren't there?
Yeah, annoyingly. Yeah. So we get into lotteries. If you have a standard 1 to 49 lottery, as we've said, and usually you want to draw 6 balls, and the player wins if they match all 6 balls. So the number of ways of drawing 6 balls from 49, not caring about the order in which they're drawn, is 49 choose 6, which if you work it out is 13.9 million and some. And that's where you might be aware of lotteries that claim a 1 in 14 million chance of winning, and that's where that comes from. But that's where we get into this thing about how many people are going to play your lottery. Because I think people sort of simplistically think, well, you just need a really low chance of winning and that'll be fine. But if you live if you sort of do a bit of market research and you reckon you're going to sell 20 million tickets, say, then a 1 in 14 million chance means you expect 1 and a bit winners a week. And the question is that good for you as a lottery company? Because in some ways it'd be great if everybody gave you £1 and nobody won anything and you got to keep all the pounds. Right? That's my business model I'm proposing. But of course people would very quickly stop playing that lottery. Because as the lottery company, what you need a constant stream of people in the newspapers. Look, this person has won the lottery and it has changed their life. You could also do this if you give me £1 next week, because you need people to keep playing. So you need, like, if you live in a country where it seems like 50 million people are going to buy lottery tickets, then a 1 in 14 million lottery is not so good, because you're going to have a bunch of winners each week.
Yeah, I mean, I guess it depends how much your prize is, and you can probably tailor that to suit. But yeah, I mean, because the other thing is you also get given a lot more pounds if you have a lot more players. So
that's true. So the more players generate a larger jackpot, but then you split it between more people. But there's something of a hype with a lottery, particularly when nobody wins one week and then there's a rollover to the following week, because then you can say it's an extra special double prize sort of week. So if you expect 5 winners a week, you're very unlikely to ever have a rollover, so you're very unlikely to ever have that sort of spiky demand for tickets and so forth. So I think from a sort of marketing point of view, you want there to be roughly 1 winner a week on average. And so what you ought to do if you're designing a lottery is you ought to start with the population of how many tickets you think you're going to sell, and work backwards from there to make the rules of the game fit your expectations for what you're going to sell. Which is why you get some of these lotteries, and the UK lotteries like this, where it's got 50 odd. Has it got 59 balls, 50 something balls? I don't play the lottery. I'm not sure.
Yeah, it was 49 and it went to 59.
Right. Yeah.
Which for some reason they described as being better.
Well,
there was a whole marketing campaign where we've changed it and it's better now.
Yeah, more is better.
And all the mathematicians were like, "Is it?"
Yeah.
Yeah.
And it costs more to play now. It costs £2 to play, so you can win a bigger. I think you can win a bigger prize now, but it's much less likely. But they've made a lot more smaller prizes.
Yeah, because this is the thing. Like, if you're talking about winning the lottery, it's often thinking about matching exactly 6 and getting the whole thing and the jackpot. But they do have quite reasonably good prizes for 5 numbers and 4 numbers. And I think, is it 3 numbers gets you a £10 note or something?
Right, maybe.
I don't know if that's still the case, but... there's something on that level where you can have a smaller prize that sort of makes you think, oh, I'll definitely play again next week because I've got £10 now, so I can buy 10 tickets.
And I find that quite interesting because sometimes the lottery seems to market itself as win the jackpot and change your life completely, quit your job, whatever it is, and which may or may not be a good thing because sort of people ruin their life by sudden changes. But anyway, so there's that sort of thing going on. But what they seem to be going with now is you're much more likely to win a few £1,000s, which is not that sort of quit your job life-changing amount of money, but it's still very nice for your pound.
Yeah.
I don't know. It's very complicated. I've been in audiences of hundreds of mathematicians where somebody at the front has asked, does anyone play the lottery? And literally no one puts their hand up, which I find fascinating.
Yeah.
Because there's this thing about mathematicians know that it's so unlikely that you're going to win that why would you play? But I remember... so around I date myself a little bit, but around the time I went to university, the UK lottery was fairly new, and every open day I went to had a talk about the odds of winning the national lottery. And every time they sort of stood up and said, "Oh, look, we're modern and on the button. We're going to give you this talk about this current topic." And you're like, "Oh no, another one!" And they were all that. They were all, "Look how unlikely it is. Please don't ever play the lottery." Kind of that sort of thing. I think, as I remember it. But I remember at university I took a game theory module, and the lecturer there had a very interesting viewpoint on this, which was, yes, it's extremely unlikely that you're going to win. And I remember having said to my mum, you play the lottery and I'll put £1 in a jar every week and we'll see who has more money at the end of the year, right? Because it's probably going to be me.
Right.
That sort of thing, I think, is why mathematicians don't play the lottery. But the game theory guy said, I could lose £1, just drop it on the street, down the drain, back of the sofa, something like that. I could lose £1 every week for a year and not notice. It would have very little impact on my life. But if I win one of these big prizes, it's going to have a huge impact on my life. So in terms of your probability of it actually happening is extremely low, but it's one of these extremely low probability but really high impact events when the cost of playing that game is negligible, really, for a sort of well-paid person to lose £50 a year playing the lottery or whatever. And I thought that's interesting. I mean, it still didn't convince me to do it. But
I sort of think about it as... because like sometimes we go to the pub and we play on the quiz machine, right? And we put some money into the quiz machine, and after an hour or so has passed, we've maybe put £3 or £4 in because we didn't quite manage to win on any of the games that we've played, but we've had a really nice time.
Yeah.
And if you go into it thinking, it's these people who go to a casino, you kind of have to say, how much am I prepared to spend on a night out in a casino? Because if I walk out of this building with no winnings whatsoever. as long as I've had a good evening, how much is that worth to me
Yeah.
in terms of money?
Yeah.
And because I remember when I was a kid, my gran used to suggest that we play the lottery, and I'm doing finger quotes right now, by just picking 6 numbers and then watching the draw, which is an absolutely terrible idea, because if those numbers had come up, the fact that we hadn't bought a ticket for them would have been completely devastating.
Yeah.
But it was a fun activity, and I think if when you buy a lottery ticket, you're going to, look up the numbers when they come out, or even watch the draw live. I don't know if that's a thing people still do anymore, but you have that kind of moment of excitement where you think, oh, I've matched the first one, oh, I've matched another one. Yeah. If that's worth £1 to you, then by all means spend £1 on it.
Yeah.
If the kind of the knowledge in the back of your head that at some point you might get that phone call, or you might find that your numbers match and be able to make a phone call to someone, then fine. But otherwise don't play.
Yeah. Yeah.
Because the chances of you winning are so small that it's practically not going to happen. And mathematicians intellectually understand this, but I think as a mathematician you can still say, actually, it's quite exciting when when you're watching the numbers come up or whatever.
Yeah.
If that's worth £1, if you enjoy that to the extent of £1, then do it.
Yeah.
And if you can't spare the £1, then don't.
Yeah, that seems reasonable. Anyway, so let's talk about the smaller prizes. So this gets quite complicated and hard to express in audio, but I will try. So with any probability, I always think probabilities like this are basically counting problems. So we're interested in the number of possibilities that we're interested in divided by the total number of possibilities. Okay. So, for example, choosing 5 numbers from 6 is 6 choose 5. So if you have a lottery where you get a prize for matching 5 of the 6, you've put 6 numbers on your ticket, and the chances of matching 5 of those, there are 6 choose 5 ways of doing that. But you've also got to think about matching the 6th number on your ticket needs to match one of the 43 that are still in the machine.
Yes.
For a standard lottery. So that means that you've got your probability is on the top half of the fraction 6 choose 5 times 43 choose 1, and on the bottom half is 49 choose 6, the number of ways of choosing 6 numbers from the machine in the first place. So the big number on the bottom, the number of ways of choosing 6 numbers from 49, is the total possibilities in the world for this outcome. And then 6 choose 5 times 43 choose 1 are the number that you're actually interested in.
Yeah.
And that comes out at 2 times 10 to the minus 5. It's quite a small probability, but not as small as the 1 in 40 million number. And so that generalises, basically. And what I would do when I'd run these workshops is I would always buy a box of sweets and some sort of chocolates that can be subdivided, individually wrapped chocolates of some sort that can be subdivided into lots of different types of prize. And then basically we would work out the probability of lots of different outcomes and say, well, look, we've got 48 balls in the machine. How many people are there in this room? And there might be like 20 or 30 or something like that. And then you think you can play around with how many balls are drawn and how many balls do you need to match to win a prize. And that can generate you different numbers of people. So, for example, if I put in 20 people in the room and 48 balls, well, 3 people will win if I require them to match 1 ball, for example.
Yeah.
But if I draw a dozen balls, then I can say, well, you need to match 4 balls out of 12 for 3 people, roughly 3 people to win, or whatever it is. And I would give the room the choice of how many winners do you want to do, and then let's make a game that generates that many winners, basically. And that's what...
Yeah, there's a chance it might go either way. Like, probability goes wrong a very predictable amount of the time, but you will probably get something in that region. And I suspect a group of people who are not familiar with this kind of probability might be impressed to see that you've managed to exactly engineer that number of winners. That's quite a nice
although if you've
outcome.
sort of taught them through it quite nicely, then hopefully they've understood where it's come from, sort of thing. And there are some rooms where they want half the people to win, and then they all take home 1 chocolate each or whatever, and there are some rooms where they want 1 person to win. And then you have to sort of say, but 1 person might not win, and what are we going to do in that? Are we going to have a rollover and run it again, or what are we going to do? So do I take it home, or do we run the thing again? Or...
Yeah, I think that means you win, yes.
Yes. Anyway, so that was good fun, but it's just quite a nice thing to think about. I think in terms of essentially probability as a counting problem. Nice bit of combinatorics.
Yeah, I'm interested in kind of how people interact with lotteries, because there is this sort of big deal, like this will be a huge amount of money if you win thing. And I think it sometimes makes people not think too hard about the maths of it. Like mathematicians obviously enjoy thinking hard about the maths of everything before they make any kind of decision. But if it's not something that you're kind of, if you're not in the headspace to do that, you can kind of overestimate how likely something is. And people get really weird about it. Like you hear these stories about lotteries where, a certain number hasn't come up for ages and everyone becomes convinced that number's definitely going to come up on the next draw, so they all buy tickets with that number. Because there's some countries where the lotteries, you don't buy a ticket with 6 numbers. You can choose to buy a ticket with 1 number, and if you match that 1 number, you win a smaller prize or whatever. And I think there was someone in Italy, there's a case like a mathematician, well, I don't know if they were a mathematician, but they made this claim that because a number hasn't come up, I think it was 253 times, or there's some specific number that it must come up on the next one. And any mathematician looking at this was no, it's still just as likely to come up as it ever is because it's one of the numbers in the machine. There's no reason why it should definitely come up. But enough people were convinced by this that people were like selling their house and buying tickets just with that number on because they were so convinced it was definitely going to come up that time. And it's like it's bankrupted people. It's been horrific.
Yeah. It's really hard to think about these things, I think. It's like the thing about if you choose 1, 2, 3, 4, 5, 6 as your numbers.
Yeah.
And if you think about that feels like that's never going to work. That's not going to come up at all. But that feeling that you have about how unlikely that is applies to every single combination of numbers.
Yeah.
It's just that this one happens to be a particularly regular one. But that you sort of have to think for yourself about that's never going to happen. And then apply that to everything else in the system.
Yeah, the likelihood of 1, 2, 3, 4, 5, 6 is just the same as the likelihood as any other combination, but you don't feel like you're expecting something that looks random. And that's what you get, but because it is random, but 1, 2, 3, 4, 5, 6 is also just as random as anything, if that makes sense. Because it could be, in a different order. So that's random. Yeah, I remember hearing an anecdote once about someone who'd raised a bunch of money to do some kind of, I think it was like a renovation of a building or something. And the person who was in charge of the project was like, right, well, we've got this amount of money now. What I'm going to do is I'm going to buy this many lottery tickets and then we'll make more money. Without checking with anyone else on the committee or without, thinking about maths for any amount of time. They bought that many lottery tickets, and obviously they won smaller prizes on some of them, but they ended up with about a third as much money as they'd started with. It was just horrific because everyone went, "You did what?" It's just like, I mean, there was a chance. There was a tiny chance that it could have resulted in a massive, massive fund for this renovation, but as it was, and I think the reason I knew about this was because someone went to this building, was like, "This building's a bit of a weird shape. It feels like it should have more rooms," and they were like, "Yeah, well, funny story." So
because there's a sort of, you can work out all the probabilities and do all that sort of thing, but also I don't know if it's, lotteries are often used, and were often used historically to raise money for things. So the king would need an army and would run a lottery to generate money, that sort of thing. And these days it's charity and good causes. So the UK lottery gives half its money to charity. So your expected winnings, if you buy a massive number of lottery tickets, cannot be greater than the amount that you've put in, because half of that's going to charity. You know what I mean? Without even doing the probabilities, as a sort of common sense.
Yeah, I think that, because that's the other thing that's a misconception. Because if it is a 1 in 14 million, say, even if you buy 14 million tickets, you're not guaranteed a winning ticket. Yeah. Right? If you buy every single possible combination, yes. Yeah. But like, you're still only going to win on one of those. So it's, and whatever the jackpot is, it won't be 14 million necessarily. So like, I think when it is a big enough rollover, I think some people have said this, that when the rollover means that the jackpot is more than the number of possible combinations, then if you have the spare £14 million to chuck in, you could buy 14 million. Oh, it's twice now, isn't it? Because it's £2 a ticket. So this is less applicable. But if the jackpot is absolutely big enough,
Well, mathematically, there has to come a point where the jackpot gets big enough that if
Yeah.
you buy every combination and win.
Yeah.
But then you don't know. The problem with that is things like other people might also win, and then it reduces your thing. And also, if you've got millions of pounds, there's probably easier ways to make more millions of pounds than this.
If the jackpot is that big, more people will be buying tickets, so the chances of someone else winning as well is higher. So I am on Twitter as @Steckles.
And I'm @Peter Rowlett.
And the podcast itself is on Twitter @MathsObjects.
We both blog at a website called Aperiodical, which you can find at aperiodical.com.
And that's also where you can find more episodes of the podcast.
And if you want to get in touch with us, you can send us an email, objects@aperiodical.com.
The music is Funk Game Loop by Kevin MacLeod, licensed under Creative Commons.